The effect of counterweight mass on trebuchet range. The idea I had for my honors project stemmed from a Mythbusters episode where they launched pumpkins using a trebuchet. The question I will be answering is, if the counterweight on a trebuchet is increased in mass, how much farther would the projectile be launched? The independent variable is the mass of the counterweight, the dependent variable is the distance the projectile is launched, and the control is the original mass of the counterweight. First, counterweight. The trebuchet was a siege engine primarily utilized from 1100 AD to 1500 AD and developed around 650 BCE somewhere in China. The first trebuchet was called a traction trebuchet and was powered by human soldiers manually pulling down parts of the machine to launch the object. The counterweight trebuchet, the more effective and modern version, used heavy objects and gravity to power its projectiles. It is a variation of a catapult and derived from the sling, and really is a combination of the two. The main difference from the catapult is the use of a sling to launch a projectile. The sling acts as a second fulcrum, adding more range and power. The physics behind the trebuchet was near perfect towards the end of its usage. The final documented use of a trebuchet in warfare, excluding modern insurgencies and rioting, was in 1521 during the siege of Tenochtitlan. The machine took days to build before finally launching its first stone. The stone went up, came down, and smashed the Spanish siege engine to smithereens. Unfortunately, however, the exact designs for a trebuchet were lost to history sometime during the 16th century. Though no longer in use today, hobbyists and other people enjoy building trebuchets for fun. In fact, there are many competitions involving the best built trebuchet. My hypothesis was, an increase in the mass of the counterweight will result in the trebuchet launching the projectile a greater distance. Procedure. My first step was to assemble the trebuchet kit I bought. The second step was to set up the experiment area, preparing the trebuchet and counterweights, and laying out materials for measuring range and setting up the camera. Third, I conducted the experiment, launching the projectiles using different counterweights and averaging the results. I then compiled the data into graphs and tables. In the upper left corner, I have the picture of the slotted weights I used as counterweights. Bottom left is the projectile, a rubber ball, and the two right pictures are of the assembled trebuchet. My experiment confirmed my hypothesis. The mass of the counterweight does affect the range of a trebuchet. With a mass of the counterweight being 1.15 kilograms, the ball was launched a distance of 3.2 meters. With a counterweight mass of 0.3 kilograms, the distance was 6.1 meters, and with a counterweight mass of 0.45 kilograms, the distance launched was 8.8 meters. I believe that my experiments confirm my hypothesis. For example, with a counterweight mass of 0.15 kilograms, the projectile was launched 3.2 meters. The data took the shape of a rough line when plotted on a line graph. Despite the shape of the line, it is difficult to come up with a mathematical formula to predict more points on the chart. The experiment was small scale and with few change counterweight masses and launch angles, so I can't draw a formula for my results. As mentioned, some of the error sources for my project stem from the size and materials used and the minimal amount of different masses for counterweights. I could improve the experiment by having a larger trebuchet, conducting more trial runs, and using more counterweight masses and projectiles. I could also devise a better system of measuring the range by using sand or flour to mark off the target area. The end.